Similarly, I will briefly introduce the compression ignition engines also. There is diesel engines. So the compression ignition engines, the only difference is dynamics to the combustion process is completely different to petrol engines. Completely different in the sense the petrol combustion, which is called the premix combustion, we mix air fuel thoroughly before the combustion is initiated. As a result of that, we need to have a homogeneous mixture. We can create a homogeneous mixture all throughout, and at the same time, in petrol combustion, as I said earlier, we'll have to maintain stoichiometric air fuel ratio in order to get the maximum benefit of this combustion process, or the maximum combustion efficiency, in other words, to obtain complete combustion. But in case of diesels, it is not like that. So if I again show you a small video clip. So the intake is more or less the same. You suck air into the system by creating a vacuum inside, if it is a naturally aspirated engine, and the flow comes through, air comes through the intake system. There is no fuel introduction at this point, because the fuel is injected directly into the system, into the combustion chamber later, and then we compress it. We compress the gas air. Now there is no air fuel mixture here. During the intake system, we don't introduce air fuel, the only air. That is the main difference. And both valves are closed and piston goes up. And when you reach the right conditions, there is a pressure and temperature, then you introduce fuel. That means you inject fuel through an injector, and this fuel penetrates into the air, compressed air within the system, and starts burning on its own. So the air and fuel, the fuel penetrates into air, and due to high temperature and pressure, the burning takes place at each and every molecule of the fuel. So that is called the diffusion combustion. Gasoline combustion is called the premix combustion, where the combustion begins at the spark plug and propagates across. But in diesels, the fuel is injected. As a result of this injection, the atomized fuel penetrates into the air molecules, and each and every molecule burns all across. Therefore, the combustion is called the diffusion combustion. In petrol engines, by controlling the throttle valve is connected to the accelerator, so we control the airflow. Now in diesels, there is no throttle valve at all in the diesel engines. So in diesel engines, the accelerator is connected to the injection system, the fuel injection system. So fuel flow system. So the petrol engines, the accelerator is connected to the airflow system, and in the diesels, the accelerator is connected to the fuel flow system. So what we control is the amount of fuel introduced into the engine. So there is no throttle valve, therefore the maximum amount of air is always sucked into the engine. So we get the full amount of air into the system, and then we decide how much of fuel is to be introduced. So there is no requirement of maintaining stoichiometric air fuel ratio, because it's not a premix combustion. Therefore, the diesel engines operate in a wide range of air fuel ratios. If you want to produce more power, then you have to have a low air fuel ratio. That means more fuel, less air. And if you want to produce a small amount of power, then you can go for a high air fuel ratio, where a lot of air and small amount of fuel. So that is the basically the air fuel, the diesel system. and there is no throttle valve in the intake system. Therefore, there is no introduction of fuel into the intake system, and there is no choke valve, and there is no throttle body, and no carburetor. That means airflow restriction in the intake system is much less. So in the petrol engines, you have many components connected to the intake system. So at each and every component, like throttle valve, carburetor, injectors, or anything like that, so there is a drop of pressure. But in the case of diesels, you don't have any of these components. Therefore, the drop of pressure in the intake system is much less. Therefore, the volumetric efficiency obviously is much higher in diesel engines than petrol engines. So there are less restriction in the intake system. Therefore, more air comes into the system. So this is the pressure volume diagram of the diesel engines, where the combustion is more or less we call constant pressure combustion. That means you atomize fuel particles burns at different points on its own. Therefore, the combustion takes place at more or less a constant pressure condition. So these things are what I just mentioned. So usually the temperature requirement to initiate the combustion is about 550 centigrades. At the time of injection, the temperature of air inside the combustion chamber is large, rather than is about around 550 centigrades. And of course, there are two technologies used in diesel combustion. One is called the indirect injection, where the combustion is initiated in a pre-chamber connected to the main combustion chamber. So this is the pre-chamber, which is in the engine head, like engine head above the combustion chamber. So the fuel is injected over here. The reason for this is, in fact, the air is pushed into this pre-chamber as the piston goes up. Therefore, the flow velocity inside this, the fluid dynamics over here is quite turbulent. Therefore, this as you inject, the injected fuel mixes or the penetrates through the air quite quickly and easily, and the combustion is enhanced within this pre-chamber. The pressure and the temperature of the pre-chamber is also high because its size is small, the volume is small. Therefore, the combustion is more smooth if you do this way. So this is called the indirect injection. This is the technology that is used in most passenger vehicles, where the engines need to be operated smoothly. And sometimes during the cold start, in the case of petrol, we use the choke, and in the case of diesels, we use something called glow plug, where you heat the air before injecting fuel. If you are familiar with, sometimes in all diesel engines, you'll have to heat the engine in the morning before starting. So heating is, there is a glow plug here. So there is a heating element which heats up the air in the pre-chamber, which enables smooth combustion. And the other technology is direct injection, where the fuel is directly injected to the combustion chamber, and the small pre-chamber is made in the piston. There's a small geometry created, volume created at the piston crown. Not the piston is not a flat piston, as you can see here. There is a small pre-chamber is created within the piston, so that you can have a higher fluid dynamics, the fluid turbulence over here, so that this mixing could be done easily, and the atomization and penetration of this fluid into air would be enhanced, so that this technology is called the direct fuel injection. Direct fuel combustion in all the engines not as smooth as indirect combustion. Therefore, the direct injection, the technology is used for the heavy vehicles like tractors and things like that, where you don't need very smooth combustion at all. But so this is the diesel combustion technology, and the diesel is in fact in this case introduced under high pressure conditions. Now in petrol engines, we introduce petrol into the intake system where the pressure is more or less around atmospheric or less than atmospheric. Or if it is a direct injection engine, direct injection petrol engine, the fuel is introduced during the intake stroke. Still, the pressure is less than atmospheric all the time. But in diesel, the fuel is introduced at the end of the compression stroke. At the end of the compression stroke, therefore, the pressure in the pre-chamber or the combustion chamber is much higher than the atmospheric conditions in diesel engines. Therefore, we have to have a high pressurized diesel injected into the system, unlike in the case of petrol engines. So petrol engines, you need to introduce fuel under atmospheric or less atmospheric conditions. But here, several times more than atmospheric conditions as far as the pressure is concerned. Therefore, you have to have a separate fuel injection system in place to maintain the high pressure. For that, of course, we use fuel injector. So the fuel injector pump, there is a separate fuel injector pump connected to the diesel engines, and this pump maintains the right pressure for injection. So the right pressure for injection is created within this fuel injection fuel pump, the injector pump, popularly known as the injector pump. And the accelerator pedal is connected to the injector pump, and the injector pump, the pressure is controlled, or the duration of injection is controlled by the injector pump, which is a purely a mechanical device. But again, when it comes to improvement of efficiency and combustion efficiency and engine size and things like that, in the later generations, this conventional fuel injection system is replaced by electronic fuel injection system that is more or less the same as EFI system in petrol. In petrols, we call EFI. The same EFI system we use in diesels are usually called common rail injection system. Common rail injection system, where you have a common rail which maintains the high pressure requirement that is for the injection in the combustion, for the combustion. So the common rail is just a name where you have a compartment up somewhere here which keeps fuel at the right pressure for the injection. So the pressure pump is there, and all the controls of this injection system is controlled by the microprocessor based system. It's exactly similar to the EFI system in petrol. Only difference is you have to maintain high pressure for injection. So the high pressure is maintained in the common rail. Therefore, that system is known as common rail injection system. So that is about the diesel injection. So the diesel, of course, the combustion characteristics depend on the spraying characteristics of injection. So the injection angle, how long we're going to inject, and the pressure and the flow characteristics and things like that decides how good the combustion process is. So those things I will discuss later on when we talk about combustion process in detail. And finally, what we discussed so far are naturally aspirated engine systems, where the intake is basically the intake air comes due to the vacuum created as the piston goes down. As the piston goes down, there is a vacuum created. So the vacuum sucks the atmospheric air into the combustion chamber. So that is called naturally aspiration, just like breathing. So these naturally aspirated engines are things that we just discussed. But if you want to produce more power, then you'll have to get more air into the system and mix more fuel with it and burn it. So as a solution, this turbocharging is introduced for both diesels and petrols. So the turbocharging is you are more or less connecting a compressor into the intake system. So rather than purely dependent on the vacuum created as the piston goes down, you suck air in mechanically by using a pump. So the compressor uh, sucks air in. Therefore, the air pressure over here can be more than atmospheric. So you create an environment where the pressure is more than atmospheric here by pumping air in. So the PV diagram, if you look at, this is the intake. The intake pressure is above atmospheric. Above atmospheric, the intake pressure is the pressure over here. So the pressure over here is above atmospheric just because you mechanically pressurize it. So earlier, if you look at the PV diagram of naturally aspirated engines that we looked at earlier, so this is the intake pressure. This is the intake pressure line, which is below atmospheric. So this is the atmospheric pressure, the environment ambient pressure, and this is below atmospheric, and this is way below atmospheric because of this throttling. And if you fix a turbocharger into the intake system, you can have intake pressure above atmospheric. That means you are sucking more air into it, and then you can mix more petrol or diesel into the amount of air that you got in, and then you can produce more power. So that is the idea behind the turbocharging. I will talk about turbocharging later on, the thermodynamics aspects as well as the operational aspects of turbocharging later. But for the moment, just for introduction, the turbochargers are usually operated, it's a mechanical system and operated by the exhaust gas flow. Usually the turbochargers are with very low friction. Therefore, the small amount of energy would rotate the turbochargers at a very high speed. So usually turbochargers turns at very high speeds. Rotational speed is around 100,000 revolutions a minute to get the boost pressure. And the problem with the pure turbocharging is when you have this kind of turbocharging, recycled turbocharging, where the turbocharger is rotated using exhaust gases, and you create high pressure also. As a result of all this, then the temperature of the gases go up. The temperature of the gases go up, intake air goes up. If the temperature goes up, then the density comes down. So when you increase the temperature of air, the air density goes down. That is a huge disadvantage in this case because, as I mentioned earlier, what we want is we want to mix, we want to burn certain amount of mass. So mass burning is what is important because the calorific value of a fuel is defined as amount of energy it releases when it burns unit mass of fuel. So you burn mass of fuel, therefore it has to be mixed with mass of air. If the density goes down, the mass also goes down. As a solution to that, the intercoolers are connected to these turbocharging systems, where the gases are cooled to some extent before it enters to the engine, so that you can regain the loss of density at the turbocharger. So usually the turbochargers are coupled with intercoolers so that the density drop of density could be maintained at a minimal possible level, but by recooling the gases so that you could get the maximum benefit of the turbocharging system. So usually it's a common jargon nowadays with these large engines, so V6, V8 engines, intercooler turbo engines. The turbocharger and intercooler should go together because of this increase of temperature or heating of air at the turbochargers. So those things we'll talk more with the thermodynamics aspects later. Diesels, of course, always there are advantages of diesel engines because the volumetric efficiency is high and the combustion efficiency is high. And of course, since the diesel is a self-ignition combustion process, we can go for a very high compression ratios with diesels, so that the thermal efficiency of engines can be increased. Therefore, there are so many advantages of using diesels as far as the thermal, the conversion of chemical energy to thermal energy or the mechanical energy is concerned. But on the other hand, diesels, to withstand these high pressures and temperatures, we'll have to make these engines with special material, and you'll have to use a lot of material to withstand the pressures and the vibrations and things like that. Therefore, the cost of engines are quite expensive. We'll have to make it very rigid, and the size of the engines are large and things like that. So those are quite sort of disadvantages. Finally, before winding up this gentle introduction to the course, the main challenge with IC engine design is usually the engines are really inefficient system. So thermal efficiency of a petrol engine or the diesel engine is in the range of 30 to 35%. So that means about 60 to 70% of energy goes to waste. So goes to waste in the form of friction, in the form of heat, and in the form of heat. So there are so many components which are rubbing components rubbing each other. So there are a lot of friction, and there are a lot of heat generated. Heat goes out, and all these things account for losses. Therefore, when you have 100% of energy, chemical energy coming into the engine, then with all these losses, the engine efficiency maximum is around 30 to 35. Under different conditions, it varies. And then there are losses in the gearbox and the drive lines and various other places. Therefore, the real outcome you can get is around maybe, it depends on the operating conditions anyway, but maybe maximum of 20 to 25%. So on top of that, there are so many other losses like aerodynamic losses and the inertia losses, the falling resistances, and many things. So those are the challenges in IC engine development. So as a result, as solutions, people move on to different solutions like hybrid engines and electric vehicles and things like that. So, but still, the IC engines are widely used as a prime mover for many automobiles, and it will continue to do so, at least for large scale engines, large size engines. The small size engines in few years time, maybe in 10 years time, will be replaced with electric systems. But the large engines like the trucks, buses, and things like that, of course, more or less, the IC engines will be used at least for another 50 years. So therefore, as engineers, we have to have, as mechanical engineers, in fact, we have to have a sort of understanding about the IC engine technology, the developments, and of course, alternative options like hybrid systems and electric vehicles and things like that. So in the coming time, I will discussing little more further on these different things that I just mentioned in this lecture. The operational aspects of IC engines, as well as the thermodynamics aspects of different processes of the IC engines. So that is the plan. So from next class onwards, I will go into this in-depth discussion on different processes of IC engines.